Okay, so in this video, we're going to go through the mock exam on the mechanics part of the course, but we're going to start off with some multiple choice questions, some of which will incorporate the looking at units part from the start of the course as well. So first off, which of these units is not a unit of power? So the correct answer is a joule second is not a unit of power, and to explain how you can work that out if you don't just know that that's the case, first of all, power is measured in watts, and a watt is a joule per second. So then 1 joule is a Newton meter, so we can turn a watt into a Newton meters per second. So we're just using the work done equation there. So you can see option A is a unit of power, and we should know that a Newton is a kilogram meters per second squared, just using F equals ma. And so we can see that option D is also a unit of power, and the only one we haven't seen so far is option B. And for those of you interested, this is actually the unit of Planck's constant once you get to that. Okay, so which of the following is a possible unit of impulse? So first thing you should know is that impulse is the change in momentum experienced by an object, which you often see in the form of this equation. So you can see an impulse is going to have the units of kilograms times meters per second, which is option B. Okay, and then next one, which of the following is a possible unit of the rate of change of momentum? So I recognize this one straight away. So first of all, in terms of y, you should know, according to Newton's second law, that a force is equal to the rate of change of momentum of an object. So you should know we're looking for a unit of force, and you should recognize the base unit of force is kilogram meters per second squared. Again, just using F equals ma or using the equation we've got above. Okay, so leaving the units questions behind, starting to get onto some mechanics. So we've got a deep space probe traveling forward at constant speed, and it's acted on by a force at right angles to its motion. What is the effect of this force on the forward speed and the sideways speed of this probe? Okay, so in terms of answering this, the information you should know that you can use to answer this is forces have no effect on the properties of motion, so displacement, velocity, acceleration, perpendicular to the force. So the forward speed cannot be changed by a sideways force, but the sideways speed, according to Newton's first law, has to change if we apply a force. So that means we want option C there. Okay, so then the mass of a fuel in a racing car decreases during the race. As a result, the lap time decreases. And this is something, if those of you who watch F1 or any other kind of racing, you will notice quite a lot. So which of the following could explain this decrease? So first of all, I'm going to show you how most people explain this, get the right answer, but their logic doesn't work. So most people will explain this. So we're going to use the equation F equals ma. They'll say, well, the force from the engine is probably about constant, so that makes acceleration inversely proportional to mass. So if mass decreases, the acceleration increases, and they go for option C. And that is absolutely the correct answer, but this logic is not allowed in terms of explaining this. So you'd get the mark and get the right answer, but your logic would be completely wrong. And the reason for that is the equation F equals ma can only be used if mass is constant. And if mass is not constant, you cannot use F equals ma. So the equation we should be using is going back to Newton's second law, which says force is equal to the rate of change of momentum. What that means is the change in momentum is the area under a force versus time graph. That's what the F delta T expression means. And if force is constant, which I agree that it is from the first explanation, that makes the area under the graph a rectangle, and I suggest you sketch it for yourself if you can't see that. And so what we get is this expression, delta mv, or an impulse, is equal to force times time. So it's from here we can get the answer C. So if we apply the same force for the same period of time, if the mass is decreased, that means you'll get a bigger change in velocity. And a larger change in velocity in the same period of time means acceleration is greater. So C is the correct answer, but you need to use the right physics principles to understand it. Okay, so what is represented by the area under a force displacement graph? So instinctively you should know it's some form of energy. So from Hooke's law we know the energy under the graph is elastic potential energy. So we should know it's some kind of energy, which means it could be either A or C straight away. So it's force and displacement. So you should know that work done is the area under a force as displacement parallel to the force graph. And if the force is constant, that means the work done is force times the displacement. So the answer we're looking for is C, work done. Okay, so in a test, a 500 kilogram car traveling at 10 meters per second hits a wall, and we have a distance of 0.3 meters in which it is brought to rest. So if we want to work out the force, we're first going to try and work out the amount of work done by the force, and then we're going to use the distance to work out what the average force is. So first thing, applying conservation of energy. We know that if the total energy or the total mechanical energy of a system has changed, work must have been done on it. And we have not been told about any changes in height or elastic potential energy. So what we're going to do is we're going to say the work done is equal to the change in kinetic energy. The final speed is 0. The initial speed is 10. So we can get the work done, and it will be negative because it's acting to reduce the mechanical energy of the car. Then what we can do is we can use, so the total work done will be equal to the average force times the total displacement. So we can divide the work done by the total displacement, and I've just quoted it as a positive number. It's against the motion, so it should be a negative number, but we're just looking for what the force is. So that's option D. Okay, so that concludes the multiple choice. Let's move on to some longer answer calculation and explanation type questions. So we've got a Soyuz spacecraft, and it's used to transport astronauts to and from an orbiting space station. The spacecraft is made up of 3 sections, and we can see we've been given the mass of each of the 3 sections. So when they leave the space station, the spacecraft is given a thrust of 1,400 newtons. Calculate the initial acceleration during the firing of the thruster engines. So we're going to assume the mass stays pretty much constant during the firing stage. Eventually its mass will start to decrease as it travels along, but we're going to say it's roughly the same, which means we can now use F equals ma, and so we're going to rearrange that. So we need to calculate the total mass, which is what you can see me doing there, and then we should round it to 2 significant figures like all the data you've been given. Okay, so Newton's third law refers to pairs of forces. State one way in which a pair of forces referred to in Newton's third law are the same. So there's a few things you could go for here. So the forces have to have the same magnitude. That's what we learn. They have to be of the same type. So if one's a force of gravity, the other one has to be a force of gravity. If one's a normal contact force, the other one has to be a normal contact force. And the 2 forces have to have the same line of action. So if we draw a dotted line extending the force arrow, they'll be the same for both of them. So one way in which the forces are different, you should know again, the forces are in opposite directions. So if one object experiences a force in one direction, the other object will experience an equal force but in the opposite direction. Okay. So when the spacecraft returns to the Earth's atmosphere, the orbital module and the service module are separated, so it's lost several parts and shed a lot of mass. The descent module has its speed greatly reduced by drag from the atmosphere. So it's being bombarded with air particles, and that's causing its speed to decrease. And we've got the 2 forces shown on the diagram. So state one reason why the 2 forces shown in figure 2 are not a pair of forces as referred to in Newton's third law. So it asks for one, but I'm going to give you lots because there's quite a few different options we could go for. So first of all, they don't have to be equal to each other. If it's slowing down, atmospheric drag is going to be greater than the weight force, so it doesn't fit the equal magnitude criteria. They're different types of forces, so one's a drag force, one's a weight force. And these two forces are acting on the same object. Newton's third law describes forces between two objects. So one of the forces will be from one object to the other object, and the other force will be coming back from that object on the first one. So again, this doesn't fit that either. Okay, so in one particular descent, the speed is reduced to 5.5 meters per second by parachutes, and the module also releases empty tanks and its shield to reduce its mass. So we know what its new mass is, 890 kilograms. A final speed reduction can be carried out by using engines and burning the remaining fuel for 3.5 seconds, and the force from that is 670 newtons. To land safely, we need the speed to be at maximum 3 meters per second. Determine whether these engines are able to reduce the speed to safe value or not, ignoring atmospheric drag because it's so slow. Okay, so first of all, again, we're going to assume mass is constant approximately during this stage. So we're going to calculate what the acceleration is using the force and using the mass. And if we assume acceleration is constant, you should know the change in velocity will be the acceleration times time. So we get that during 3.5 seconds, the speed is going to change by 2.634, and it's going to decrease by that. So change in speed will be the final speed minus the initial speed. So the final speed will be the initial speed plus the change. The change is negative, so we're going to subtract it, and we get 2.9 meters per second. So the engines can reduce the speed to a safe landing speed. Okay, so new question. A cricket ball traveling at a speed of 32.5 meters per second is hit by a bat, and after the impact, the ball has the same speed but is traveling in the opposite direction. The mass of the ball is 0.156 kilograms. Calculate the change in momentum of the cricket ball and giving an appropriate unit. So change in momentum, also known as an impulse, will be calculated by doing the mass times, because it's constant, times the change in velocity. The initial velocity I'm going to say is plus 32.5, which means the final velocity in the opposite direction is minus 32.5. We subtract the initial speed, and so essentially we're going to get 2 times the speed as the change, and that gives us an impulse of 10 Newton seconds, or we could have given it as kilogram meters per second. Either would be appropriate. So the bat is in contact with the ball for 3.80 milliseconds. Calculate the force exerted by the bat on the ball. So force is equal to the rate of change of momentum, which means the impulse will be equal to the force times by the time, assuming the force is constant. So we know what the force times time is. We've just calculated it. So if we divide it by the time, we can get what the force is, which is what you can see there. Okay, so moving on to question 10, we're going to look at kiteboarding, which is where we use a sail type device to go at high speed across water, usually, or you can do it on land too. So we've got wind blowing the kite, and the kiteboarder moves at constant speed across a level water surface. So it's traveling horizontally, and the tension is 720 newtons, but it's at 50 degrees to the horizontal. Now we want to calculate the vertical component of tension, which we're going to use in the next question. So if you look at the bottom left, that's my triangle where I'm resolving 720 into 2 components using trigonometry. So then what I'm going to do is I want the vertical component, so that's going to be 5.5 times 10 to the 2 newtons to 2 significant figures. The next question, a kiteboarder has a mass of 58 kilograms. Calculate the normal reaction of the board on the kiteboarder, so the normal contact force. So first thing is, this person is traveling at constant speed, and they're traveling horizontally. So what I've done is I've used the fact the resultant force in the vertical direction is 0. So that's the starting point here. So that means the forces upwards must equal the forces downwards. So the only downward force would be the person's weight force. The 2 upward forces will be the vertical component of tension, and the normal contact force R. We want R, so we're going to rearrange it to make that the subject, plug the numbers in, and we get a value of 17 newtons. Okay, so suggest how the answer to part 2 compares with the upthrust of the water on the board. So I'm going to go through the same process again. The board is traveling horizontally, so the vertical resultant force must be 0. So that means the upthrust from the water must be equal to the downward normal contact force the board is experiencing from the person. So the reason that I know that there is this force downward, so Newton's third law tells us that if the board exerts an upward normal contact force on the rider, which is what we had in the previous question, the rider must exert a downward normal contact force of the same magnitude on the board, but the board isn't accelerating downwards, so the upthrust must be equal to that value. Okay. So now we're going to use the kiteboard on a ramp, and the end of the ramp is 1.8 meters above the water surface. The final velocity when you leave the ramp is 12 meters per second at an angle of 17 degrees to the horizontal, and the kiteboarder lets go of the line the instant they leave the ramp. So there's no tension anymore, it's only the weight force accelerating the person because we're ignoring air resistance. And we want to calculate the speed with which the kiteboard enters the water. So I'm going to show you two different ways people would solve this question. My preference is the second one, but I'll show you both. So first off, we need to split the speed of, or the velocity of the rider into two components. So I've used a vector to express that. So the horizontal component is 12 cosine 17, the vertical 12 sine 17 upwards. So in the vertical direction, the speed is going to change because it's being accelerated by gravity, and we can calculate what its final velocity will be in the vertical direction, and it's going to be 6.901 downwards in the end. So we know that the horizontal component of velocity is not going to change because there's no force acting horizontally. So then when we use Pythagoras, we can find out what the final speed is, 13 meters per second. So that's the first way we can do this, which we have to split it up into components and mess around with Pythagoras, which I don't particularly like. It's fine, but it's not the easiest way. So the way I would do this is using conservation of mechanical energy. So once the person releases the kite, the person is no longer having any work done by external forces. So that means the total mechanical energy before must be equal to the total mechanical energy afterwards. And what I've done is I'm going to use the landing on the lake as 0 GP. So they have no GP at the end, but they start with some, and they start with some kinetic energy. So first off, we then put in the equations for each of these types of energy. We can cancel out the masses and then make V the subject, and we plug the numbers in and we get exactly the same answer, but we haven't had to resolve and we haven't had to use Pythagoras. Okay, so moving on to have a look at a roller coaster track. So the car is initially at rest at A and is lifted to the highest point of the track, B, which is 35 meters above A. The car with passengers has a total mass of 550 kilograms, and it takes 25 seconds to lift the car from A to B, starting off with negligible 0 velocity. And then once it reaches B, it goes unpowered along the track. And this is very typical of the way roller coasters work. So calculate the power used in lifting the car and its passengers from A to B, including an appropriate unit. Okay, so first off, I'm going to work out how much work must have been done by the powering system. So when it reaches the top of B, it's going to essentially change the GP. So that's what we're going to have to do work for. And we can calculate the change in GP, which is there, and that's the amount of work we've done. And the average power would be the work done divided by the time over which that work is done, which is going to be essentially given by this expression, and we're given the unit of watts because it's a unit of power. Okay, so then moving on to the next one. So the speed reached by the car at C at the bottom of the first dip is 22 meters per second, and the length of the track is 63 meters. Calculate the average resistive force acting on the car, giving an appropriate number of significant figures. So I'm going to use the same process again. So this time we've got two forms of energy changing. So we've got work done by a resistive force, but we've got GP that's decreasing as it's going down the hill, and we've got kinetic energy that's increasing because it's accelerating. So the first thing I'm going to do is calculate the work done by the resistive force. So change in GP is a negative number because it's decreasing. Change in kinetic energy is a positive number because it's going from 0 up to that value. So that's the work done. And to calculate the average force, we're going to use the total work done divided by the total distance travelled, giving us a total force of 8.8 times 10 to the 2 newtons, but it will be negative because it's acting against the motion there. And we give it as two significant figures because the data we've used in the question, the 22 and the 63, are two significant figure numbers. So explain why the resistive force is unlikely to remain constant as the car descends from B to C. So the two forces I thought about in my answer were air resistance and friction, which are the most likely two candidates. So air resistance depends on speed, and we know the speed is increasing as it accelerates. So air resistance would increase as it went down the track. So that's the first one. So as it's going down the track, if you look back at the diagram, you'll see the angle of the slope changes, which means the normal contact force is changing because the normal contact force is given by mg cosine of the angle of the track. So friction also depends on the normal contact force. It's directly proportional, in fact, to the normal contact force. So if the normal contact force changes, that means friction will also be changing. Okay. So at sea, a passenger of mass 55 kilograms experiences an upward reaction force of 2,160 newtons when the speed is 22 meters per second. Calculate the radius of curvature of the track at sea, assuming the track is circular. So first of all, if you haven't studied circular motion, which most people do in the upper sixth yet, you will not be able to answer this question, so do not worry if you don't understand what the hell's going on. For those of you who have studied circular motion, should be able to answer this question. And so first of all, you need to calculate the resultant force acting on the car, and that's going to be the upward reaction force minus the weight force. So that's the resultant force. And when you study circular motion, you learn that the resultant force must be equal to the mass times the velocity squared divided by the radius of the circle you're traveling in. So we can rearrange that to make r the subject, and that gives us a radius of curvature of 16 meters. So the exam paper I took this from gave the answer as 12 because the mark scheme was wrong because they didn't calculate what the resultant force was. So do watch out for that. They are occasionally incorrect. Okay, so now we're going to do some projectile motion with cannonballs. So we're in a castle. We've got a cannon and we're firing at enemy ships that are presumably trying to attack. And the horizontal distance is 150 meters to the ship. It's 67 meters downwards to the water. So show that the time taken for the cannonball to reach the water surface after being fired from the cannon was 3.7 seconds, ignoring air resistance. So we're going to look in the vertical direction specifically, and we don't know the final speed, so that's why I've picked s equals ut plus half at squared. In the vertical direction, initial speed is 0 because it's fired horizontally. So we can calculate, therefore, the time using the vertical displacement and the vertical acceleration, which is gravity. It gives us an unrounded answer of 3.69, so that's going to be 3.7 to 2 SF, which is appropriate. Calculate the velocity at which the cannonball was fired. So we know the time that it was in the air, and we know the horizontal distance, so therefore we can work out the velocity using this equation and the fact acceleration is 0 in the horizontal direction. So we can rearrange that. So horizontal distance is 150, the time is still 3.69, that gives us a speed of 41 meters per second. calculate the vertical component of velocity just before the cannonball hits the ship. So now we know the time. There's a few ways of doing this, but I'm going to use this equation here. So the initial speed, again, we know is 0. We know the acceleration and the displacement in the vertical direction, so we can work out the final velocity, and it actually should be minus 36 because it's downwards. So by calculation or scale drawing, I'm not sure how many of you will do scale drawings, but I guess you can if you want. Find the magnitude and direction of the velocity just before it hits the ship. So first of all, I'm going to use Pythagoras to find out what the velocity is. I'm not going to draw it and measure the hypotenuse. So these were our two components, 36 and 40. So square them, add them, square root gives us 54 meters per second. To get the angle, I'm going to give the angle to the horizontal, and I'm going to use tan because we know two components of it. So the vertical component, or the side opposite, will be the 36, which is actually minus 36. The horizontal component, or the adjacent side, is going to be the 40.5. So it's going to be 42 degrees, and that's below the horizontal. Okay, so finally, calculate the loss of gravitational potential and energy of the cannonball. So a nice easy question to finish off. We're just going to use the pretty standard equation for this, and that gives us a value of 1.4 times 10 to the 4. I've not put the minus sign in because it asked us to calculate the loss in gravitational potential energy, so that's why the minus sign isn't there. And then finally, describe the energy changes that takes place from the moment that the cannonball leaves till it hits the water, including air resistance. So first off, the easy one, we know we're transferring GP into kinetic energy. That's why it's speeding up. But we're also transferring GP into internal or thermal energy in the surroundings. That's what air resistance does. It transfers mechanical energy to thermal energy, which we'll start calling internal energy later in the course, which is why that's there. Okay, so that finishes this review of this mock exam on mechanics. If you have any questions, please feel free to comment and let me know. I'll try and get back to you as quick as I can, but thank you very much for taking the time to watch.